Hi everyone and welcome to this short video about vectors. After doing a lot of analysis topics in the past weeks, we will continue with linear algebra now. And in this week you will get to know the basics. In this particular video we will talk about the most important building block that you will need, which are vectors. Therefore, in this video you will get a general understanding of what vectors are. We will also talk about different vector operations which enable us to really work with them. Linear independence is of special importance here and will most certainly stay present in the content during the next week. And we will also talk about spatial relations of vectors and finally get to know some examples and real-world applications where vectors are useful. And with that being said, let's start. First of all, I want to motivate this topic with an example. Let us all imagine that the pandemic is finally over and we are going to a party. At this party, there are 3 big vessels filled with cocktails. And all of the cocktails contain the same ingredients: orange juice, lime juice, gin, and vodka. The 3 cocktails, let's call them C1, C2, and C3, however, have different proportions of these ingredients. In cocktail 1, we have 1 portion of orange juice, 2 portions of lime juice, 7 portions of gin, and 4 portions of vodka. In the second cocktail, we have something more for the fruity people among you. It has been mixed with 9 portions of orange juice, 5 portions of lime juice, and 1 portion of gin and vodka each. And then there's also cocktail 3, which is the strongest one for the really alcohol-loving people here. It contains 2 portions of orange juice, 1 portion of lime juice, 8 portions of gin, and additionally also 9 portions of vodka, which makes in total a whole lot of fun. You can already see that we found a nice and easy representation of these cocktails with the notations in the brackets. Now, the set of all possible cocktails that we can mix with these 4 ingredients, orange juice, lime juice, gin, and vodka, is called the vector space. The 3 cocktails from the examples C1, C2, and C3 are then called vectors. Now, with this concept of vectors and such kind of representation, we could do a lot of interesting things. For example, we could mix cocktails together and could try to create one that perfectly fits your taste. Let's say you want to have a cocktail with the proportions 1, 1, 1, and 1. One big question in linear algebra and when working with vectors is under which circumstances we can find a solution here. This solution would then tell us what we need to do and how we need to mix the cocktails, meaning how much of which cocktail we need to pour together in order to get our desired cocktail with the proportions 1, 1, 1, 1. So far for the motivation and why vectors are useful representations. But let's continue with a more general description now. An n-dimensional vector v is defined as a n-tuple, so it has n elements denoted with v1, v2, and so on until vn, which you write in one column in parentheses. v1, v2, and so on are all elements of the real numbers. Now, the set of all these possible vectors with this definition is called r to the power of n. So we have an n-dimensional space, and on each axis we have the real numbers. While it is easy to imagine spaces with 2 or 3 dimensions, I know that it can be hard to imagine spaces with more than 3. But you can imagine it like this. Each axis has a specific meaning, like in the cocktail example. There we also had vectors in a 4-dimensional vector space. So you can simply imagine that each row of the vector is represented by a different axis. So far so good, but maybe you have also seen vectors in another representation before. A vector can also be defined as a geometrical object which has a magnitude and a direction. Therefore, they are often drawn as arrows, as you can see in the little sketch here. A vector always connects 2 points in space, and the term magnitude refers to the length of the vector, and the direction obviously refers to the direction it points towards. Now, where in the space the vector is located is actually not important. All that matters is the magnitude and the direction. And therefore, 2 vectors are equal if they have the same magnitude and direction. So the equality holds independent of the position in space. If we describe a vector from the origin to some point P in space, the vector can solely be described by the coordinates of the point P. And this is also what matches the representation from the last slide. Maybe you've also seen the notation of a vector with a small letter and an arrow on top before. This is often done because you can then immediately see that it is a vector. But for us, it is also totally fine to write them without, like in the sketch here. So we just denote the vector with a V and leave out the arrow on top. In the next weeks, you will most likely not encounter this arrow-like context of vectors a lot anymore. This is the case because in core mathematics, vectors are defined more generally like elements of a vector space. And what exactly a vector space is will be covered in the next week. I have mentioned before a few things about them, for example in the cocktail example. There, the vector space is the set of all possible cocktails that can be mixed with our ingredients. Let's recap what we know so far. Vectors enable us to represent data in a higher dimensional space. They belong to vector spaces and we can calculate cool things with them. But how does this work? Let us take a look at different vector operations now. How addition, subtraction, multiplication, and so on work with usual numbers should be clear. But now we have vectors instead, so we have several dimensions, which means several rows. Therefore, we also need to define mathematical operations for vectors, because we cannot simply use the rules we had before. Let us start with addition. When you want to add two vectors, you have to do this element-wise, or maybe row-wise or axis-wise would be the better word. The first vector here has the value v1 in the first dimension and the value v2 in the second one. The vector we are adding has the value u1 for the first dimension and u2 in the second one. Now the solution here is simple. We simply use normal addition per row. So in the solution we have v1 plus u1 in the first dimension and v2 plus u2 in the second dimension. For subtraction, it works the same. But this should be clear because subtraction can always be represented as some kind of addition. So we also do it row-wise here. Therefore, we end up with v1 minus u1 in the first row and v2 minus u2 in the second row. Now onto scalar multiplication. Last week, you already got to know the term scalar in the video about groups. A real number or an element of a field is called a scalar, so it is one-dimensional, basically just a number therefore. Opposed to vectors, a scalar does not have a direction, but it has a magnitude, which is the number it has. In the example on the slide here, lambda is a scalar. It is a number that comes from the field which defines our vector space. This might have sounded a bit strange. So if we would have the vector space R2, so the real numbers two-dimensional, the scalar lambda would be an element of R, so a real number. It is called a scalar because we can scale with it. Let us finally talk about the mathematical operation here. Scalar multiplication is defined as follows. If we multiply a scalar lambda with the vector v1, v2, we end up with lambda times v1, lambda times v2. So what we do here is multiplying this scalar to each row. This means we scale the whole vector. If you think about this in space, scalar multiplication does not change the direction of the vector. It just changes the magnitude because it scales the length of the vector. The last rule here is the dot product. With dot product, we refer to the multiplication of two vectors. The rule here is that we do row-wise multiplication, but the solution is then not a vector anymore, but an actual number, which is the sum of all these row-wise multiplications. So if we multiply the vector v1, v2 with the vector u1, u2, we will end up with v1 times u1 plus v2 times u2. Note that these examples here use two-dimensional vectors. All the rules here, of course, also apply for larger vectors. Because you should really try to memorize these operations, let us calculate some examples now. Here you can see 4 exercises. You can pause the video now to calculate them on your own with the rules you just learned. We will go through the solutions and the intermediate steps together on the next slide. Here you can see the solutions to the exercises from the previous page. In the first task, you had to add the vectors 1, 2, and 3, 4. The rule stated that you have to perform the addition row-wise. And therefore we have 1 plus 3 in the first row and 2 plus 4 in the second one. And therefore we will end up with the vector 4, 6. In the second exercise, you had to perform subtraction, and the vectors were the same as the ones from the first exercise. So this works row-wise again, and therefore we have 1 minus 3, which equals minus 2 in the first row, and 2 minus 4, which equals minus 2 in the second row. In the third exercise, you had to perform scalar multiplication. The task was to multiply 5 with the vector 1, 2. And the rule stated that you have to multiply the scalar to each row, and therefore we have 5 times 1 and 5 times 2. And this will result in the vector 5, 10. Now, the last task was to calculate the dot product between the vectors 1, 2, 3 and 4, 5, 6. It's a dot product because you multiplied 2 vectors. And the rule here stated that you have to do this element-wise again, and to add up all the results. So what you do is that you multiply 1 times the 4 for the first row, which is 4, and you add 2 times the 5 for the second row, which is 10, and 3 times 6 for the last row, which is 18. So you will add up 4, 10, and 18, which is 32 in total. One of the most important concepts that we are dealing with when talking about vectors is linear independence. A set of vectors can either be linear independent or it can be linear dependent. Let us talk about independence first. A set of vectors is called linearly independent if there is only one linear combination of these vectors that produces the zero vector. All scalars are zero in this case. The zero vector is the vector that has 0 as entry for each dimension. So if we are, for example, in a 3-dimensional space, the zero vector would be 0, 0, 0. And with linear combination, I mean that we linearly combine the vectors from our set of vectors. This means adding them and weighting them all with different scalars. Let us take a look at this in a formal definition. Suppose we have the 3 vectors u, v, and w that are all elements of the vector space R3, and we have the scalars a, b, and c, which are elements of the real numbers. Now, we linearly combine them by adding u, v, and w, and we weight each of the vectors with a scalar. With this linear combination, we want to produce the zero vector, so 0, 0, 0 in this case, because we are in the space R3. Now, if we know the vectors u, v, and w, we simply need to find the values for the scalars a, b, and c, so that the solution is actually the zero vector. If the only result to this solution is the trivial one, which means that all scalars are set to 0, then the vectors u, v, and w are linearly independent. And this is already all that matters for linear independence. We linearly combine the vectors and search for scalars that fulfill our equation, scalars that yield to hitting the zero vector. And if there's only one solution, namely the trivial one where all scalars are set to 0, then and only then the vectors are linearly independent. But now onto linear dependence. As you may have guessed already, linear dependence is the opposite of linear independence. Formally, this means that we can combine a set of vectors in a non-trivial way to produce the zero vector. So, setting all scalars to 0 is not the only solution anymore to produce the zero vector, but there's also at least one more solution that produces the zero vector. But there's also another cool thing that comes with linear dependence. If a set of vectors is linear dependent, it also means that at least one of the vectors of the set can be produced by a linear combination of the other vectors. In the case of linear independence, this is not possible. All vectors contain some information or some part that cannot be described by the other ones. Let us look at two examples now. Here you can see linear combinations of different vectors to produce the zero vector. In the first example, we have the vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. And we weight them with the scalars a, b, and c to hit the zero vector. And as you can easily see here, the only solution would be to set a, b, and c to 0. And therefore, the three vectors are linearly independent, because there's no other way we can combine them so that the zero is reached in each dimension. If you look at this in more detail, you can see that in the first dimension we have a 1 for the first vector and zeros for vector 2 and 3. But if we want to have as a result the 0 in the first dimension, we have to set a to 0, because otherwise there is a number in the first dimension in the result. And this is also the same for the second and third dimension. If we want to have a 0 in the result, we have to set b and c also to 0, because otherwise there would be numbers. So the only solution is the trivial one here, setting all three to 0. Now let us take a look at the second example. There we have different vectors. The first one is 1, 1, 1. The second one is 1, 1, 0. And the third one 0, 0, 1. And of course we also want to check if we can hit the zero vector with some kind of linear combination using the scalars a, b, and c. And here there's more than the trivial solution. Of course it would also work to set a, b, and c to 0, but if you, for example, would set a to 1, b to -1, and c to -1, it would also hit the zero vector. Because for the first dimension we would then have 1 minus 1 plus 0, which would be 0. In the second one again, 1 minus 1 plus 0, which is 0. And in the third one, 1 minus 0 minus 1, which is also 0. And therefore, we have a non-trivial solution and the vectors are linear dependent. This also means that two of the vectors can produce another one, or at least one of the vectors can be reproduced by the other ones. And here you can easily see that the first vector could be produced by adding the third and second vector together. Now, you already saw these two examples, which were quite easy when you took a closer look at them. But more on how to solve such equations for more complex cases will be covered in the next video, where we will talk a lot more about systems of linear equations, which are quite helpful when you have such a problem as finding out whether vectors are linear independent or dependent. Now let us talk about spatial relations. There are different things related to space and spatial relations that we can calculate for a vector or for different vectors together. The first thing I want to talk about here is the length of a vector. We denote this by two vertical lines, so one in front of the vector and one behind. And the formula for calculating this is that for each element of our vector, so each entry that is written in the parentheses, we square this, and we add all of these up, and finally we take the square root out of them. And therefore the formula here is the square root of the sum that starts at I equals 1 and runs until n of the entry vi squared. The second concept I want to talk about here is orthogonality. Orthogonality means that the dot product of two vectors is 0. And if two vectors are orthogonal, this means that they are perpendicular to each other, which means they are in a right angle. And this is the case when, as I just said, the dot product is 0. And this orthogonality is quite easy to visualize in a two-dimensional or three-dimensional space, because then you can just imagine two vectors are standing in a right angle to each other. But in higher dimensional spaces, this also gets quite interesting, because It can be perpendicular, so in a right angle for some dimensions, but for the other dimensions, the vectors could actually be quite close to each other. The third spatial relation here is the angle between two vectors. So the angle theta between two vectors u and v is calculated by taking the arcus cosine of the dot product of the two vectors divided by the product of the length of the two vectors. And the last spatial relation I want to talk about here is the Euclidean distance. First of all, I want to mention that there are different distance measurements to calculate the distance between two vectors or two points in space. But when we are only referring to the term distance or use the term distance, this usually means we are talking about Euclidean distance. But keep in mind that there are also other distance measurements, but most interesting to us is the Euclidean distance. So the formula for it is that the distance between the vectors u and v is defined by the length of the vector u minus the vector v. And therefore the formula is the one from the length that you had before, just that you plug in the vectors subtracted from each other now. And if you remember the calculation for a subtraction of two vectors, it's precisely that you do element-wise or row-wise subtraction, and therefore inside of the sum we now have ui minus vi. To recap the rules you've just learned, I have some exercises prepared for you. And here you have given the two vectors u, which is 1, 2, 2, and the vector v, which is 3, 0, 4. And your task is now to calculate the length of both vectors and to find out whether they are orthogonal, to calculate the angle between them and the distance between the two vectors. And I would highly recommend that you solve the exercises on your own and pause the video now. But on the next slide, we will also go through the solutions together step by step. So don't worry if you don't feel that comfortable with the calculations yet. And here you go with the solutions to the 5 exercises. In the first task, you had to calculate the length of the vector u. So if you remember the formula for the length, you had to square all of the entries of u, add them together, and take the square root of them. So therefore, we have the square root of 1 squared for the first entry, so in the first dimension, 2 squared for the second entry, and also 2 squared for the third entry. And therefore we have the square root of 1 plus 4 plus 4, which is the square root of 9, which is 3 in total. And for the length of v, this works the same, just that we use different numbers, because we have 304 instead of 122 here. So we have the square root of 3 squared plus 0 squared plus 4 squared, which is the square root of 9 plus 16, which is the square root of 25, which is 5 in total. In the third exercise, you were asked to check whether u and v are orthogonal to each other, which means that they would have a right angle and be perpendicular to each other. And what we have to do here is to calculate the dot product and check whether it is 0, because only if it's 0, only in this specific case, the two vectors would be orthogonal, otherwise they wouldn't. So the calculation for the dot product was to do element-wise or row-wise multiplication and to add up all the results. Therefore, we multiply 1 times 3, which is 3 in the first dimension, 2 times 0 in the second dimension, which is 0, and 2 times 4 in the third dimension, which is 8. So we have 3 plus 8, which is 11, and 11 is obviously not 0, and therefore u and v are not orthogonal to each other. Let's continue with the fourth exercise now. There you were asked to calculate the angle between the vectors u and v. Now, from the third exercise, we already know that the angle is obviously not 90 degrees because the two vectors are not orthogonal to each other. But luckily, we can use the formula for calculating the angle that you saw on slide 11. So the formula was to take the arcus cosine of the dot product of u and v divided by the product of the length of u and v. And all the steps, the parts that we need for this equation are already given in the task 1, 2, and 3. Because we know that the dot product is 11 from the previous task, so task 3, and we know that the length of u is 3 and the length of v is 5. And therefore we have the Arcus cosine of 11 divided by 3 times 5, which is 11 divided by 15, which is in total 0.748 in radians, and this would result in 42.83 in degrees. And if you're not comfortable with the conversion here, you should go back to a few weeks ago where we covered this formula for the calculation of radians to degrees. The last exercise given here was to calculate the distance between the vectors u and v. And the formula here stated that we have to take the square root of the subtraction of the vectors u and v. So if we would subtract the vectors u and v, we would have 1 minus 3 in the first dimension, and 2 minus 0 in the second one, and 2 minus 4 in the third one. And therefore we have to take the square root of 1 minus 3 squared plus 2 minus 0 squared plus 2 minus 4 squared, which is minus 2 squared plus 2 squared plus minus 2 squared, which would be the square root of 4 plus 4 plus 4, which is the square root of 12. And this should be 3.464 in total. And because this video was a lot of theory and it can be hard to imagine vectors in space and when to use them, when they're useful, I want to give you some examples now of when vectors are actually used and when they are quite useful for us. The first example here is the cocktail example you already saw in slide 2. And there we could nicely represent different ingredients and the proportions of them in vectors. But be careful, because in this example here, negative values do not exist, because you cannot simply use a negative amount, for example, of orange juice inside your cocktail. So you can only use positive numbers, or maybe also the 0, but negative values do not exist in this case. The second example that is quite useful is data vectors. In a data vector, each entry or axis stands for a different data field. And this is actually super useful in cognitive science. For example, when you want to represent a large amount of data that belongs to one participant in an experiment. So each participant or each trial could be represented by one data vector. And the third and last example here of when vectors are frequently used is in physics and in engineering. And there, for example, you could represent the speed or a movement in one direction by a vector. And therefore this is super useful and you might have seen that already in high school. And that's already it for this week's video about vectors. By now you should know what a vector is and how they are represented. You should also be familiar with different vector operations, including addition and subtraction of two vectors, scalar multiplication, and the calculation of a dot product. The concept of linear independence and linear dependence should also be clear by now. However, how to calculate and check for them should be easier after watching the next video about systems of linear equations. Finally, you should also be familiar with some concepts of spatial relations regarding vectors and how to calculate them, including the length of a vector, the angle between two vectors, the concept of orthogonality, and the Euclidean distance between two vectors. I hope you like this one and see you again next time.